Uh, Good afternoon to all the participants. We are back for the 6th session of our international webinar series on applications of mathematics. So I would like to thank all participants for being with us for all the sessions. We are receiving very good response from everyone. So for this session, we have Dr. Manjil Saikia, who is doing postdoctoral research in Cardiff University, United Kingdom. And he's very active in mathematical activities, mathematics Olympiads and research, as well as organizing lectures, delivering lectures. So he's quite a well-known face here. So I'd like to welcome him. Yeah, Manjil, you are on screen.
Thank you, Devasis. It is very nice to be here.
Yeah, it's very nice to have you for our program also. I am inviting on screen our head of the department, Dr. Biplab Chaudhary. Hello, sir.
Hello. Hello.
Hello.
Okay, sir.
Hello. Hello.
Sir, we are already live with the lecture. So Dr. Manjil Saikia is also here. I'd like to invite our student, Shubhadeep Pal, to kindly read out the biodata of our speaker, Dr. Manjil Saikia. Yeah, Shubhadeep, you can start.
Yes, sir. Hello, everyone. I am Shubhadeep, a student of Mathematics Honours, Gurucharan College. I am honored to introduce our prestigious guest speaker, Dr. Manjil Saikia, for this session. Dr. Manjil Saikia is a postdoctoral researcher at Cardiff University, United Kingdom. He did his master's in mathematics from Tezpur University and a postgraduate diploma from International Centre for Theoretical Physics, ICTP, Trieste, Italy. He was awarded PhD in mathematics from University of Vienna, Austria. Dr. Saikia is the co-founder of the popular mathematical Ganit Sora, which publishes math-related articles and information. His research interests are in enumerative and algebraic combinatorics, number theory, and analysis of algorithms. He has been instrumental in organizing several talks and webinars by eminent resource persons through Ganit Sora. He has also been closely associated with the mathematical Olympiad activities in Northeast India. Looking forward to an interesting lecture by Dr. Manjil Saikia. Over to Devasis sir for continuation.
Thank you, Shubhadeep. I am putting you backstage now. So we'll continue with the session. Meanwhile, we also have Dr. Anirban Roy, our earlier speaker, and also Dr. Vishwajit Dev, whose session we enjoyed in the afternoon. So yeah, it's in the last session also I mentioned that it's very nice that this particular international webinar series is being viewed or observed by resource persons as well. Means resource persons are attending other resource persons lecture. That's a very nice thing. Usually this is not seen in many of the seminars. So that's a very good thing. They are participating in every talk. So as of now, I'm putting everyone on backstage, and we'll begin with Dr. Manjil Saikia. So for the participants, the rules are yeah, I request you to kindly post your questions and all in the comment section, and we'll take up those with the speaker. And the feedback form will be provided at the end of the session. And some of the participants are mailing about not finding feedback form. The forms are available in the comment section of all the videos. For all the videos, I have made available the form in the comment section. Please go through the comment section nicely, and then contact me even if you do not find it. Okay? So it's over to Manjil, sir, for your presentation. You can share your screen.
Thank you so much, Devasis. So let me just share.
Yeah.
Okay. So, I think you cannot see it, right?
No. As of now, I'll get a notification here, and then I'll have to add it to the stream. After clicking the share option, you'll see there is a dialog box will come, and below you will get a blue button, share screen. So just click on that share screen and
so it seems that
choose share enter screen. Yeah.
yeah, it seems that due to my computer settings, I cannot do it now. So I have to leave the meeting and I'm coming back again. Okay.
Oh, okay. Yeah. Yeah. So Manjil sir will be back soon after changing some settings. Okay. So let us wait for some time.
Okay. So let me try again.
Yeah. You please try that share screen. There's an option.
Yes, I think now you can see the screen, right?
Yeah, it's available now. Add to stream. Yeah, the screen is visible. You can open the presentation.
So let me just.
Yeah.
So is it full screen now?
Yeah, it's full screen.
Okay. So
Yes, you can go ahead. Yeah.
Can you tell me how much time do I have in total?
Yeah, 1 hour. 1 hour, and then we'll have the question answer sessions. Yeah.
Okay. So thank you so much, Devasis, for this very kind invitation.
Thank you.
And also, it is a pleasure and an honor to give the talk along with so many nice researchers. And all the talks have been very nice so far. And I think it is a commendable job that you have done. So congratulations from my side.
Thank you.
And thank you, Subhadeep, for the very nice introduction. So let me just say that before I begin that my talk would be probably slightly different from the other talks because I am going to show some of my results in the later part of the talk. But in the beginning, it will be a general like introduction to one of the topics that I work in, called alternating sign matrices. So in between, I'll maybe around halfway mark, around 30 minutes from now, I'll stop. And if there are any questions in between, then I can take those. Because it is very important that the first part is understood. Otherwise, the second part, the audience might get lost. Anyway, so the title is the remarkable sequence 1, 1, 2, 7, 42, and so on. And why is this sequence remarkable? I'll try to explain a bit about that. And I'll focus on one of the objects that this sequence counts, mainly alternating sign matrices. So let's see. The sequence in the title is actually given by a very nice formula, very nice mathematical formula. And the formula is the following. So you have a bunch of factorials in the numerator as well as in the denominator. So what do I mean by nice formula? You can see that the nice word is in quotes. So I am a discrete mathematician and I work with discrete structures. And one of the questions that I try to answer is that given some sort of structure or a collection of combinatorial objects, is there a nice formula which counts those objects? And for me, a nice formula would be a formula of this type, where the numerator as well as the denominator is a product of factorials, or it might also be that in later slides you'll see that there are formulas where the formula is written in terms of sum of products of factorials. So in that sense, this formula is nice, and I'll explain why this formula is nice in some subsequent slide, how to actually get this formula and so on. So I mean, anyway, so let's see. So in compact product notation, the above formula, you can write it in this way. So the numerator is now 3j plus 1 factorial, and the denominator is n plus j factorial, and j runs from 0 to n minus 1. So this is a compact version of the formula. And if you put n equal to 1, then this is an empty product. So the empty product for me will always be taken as 1. Okay, so if n is equal to 1, then you get 1, and if n is equal to 2, then this is just a product of two terms. The first term will be 1 factorial divided by 1 factorial, so that is just 1, and the second term would be now 3 plus 1 factorial divided by 2 factorial, so which will give you 2. So the second term in the sequence was 2. So the first term corresponds to n equal to 0, the second term corresponds to n equal to 1, and the third term corresponds to n equal to 2, and so on. So n equal to 3, n equal to 4, and so on. Okay. So this formula was actually conjectured by three people, Mills, Robbins, and Ramsey, to count what are called alternating sign matrices. So they first defined alternating sign matrices, and then they conjectured that the number of n times n alternating sign matrices is given by this formula. And this was in the 1980s, early 1980s. So let me define an alternating sign matrix. An alternating sign matrix of size n is a square matrix, n cross n matrix, with entries in the set 0, 1, and -1. And there are certain conditions that the matrix has to satisfy. The first condition is that all row and column sums are equal to 1. And the second condition is that the non-zero entries, they alternate in each row and column. So that means if there is an entry which is 1, then the second non-zero entry in that row cannot be a 1 again. It has to be a -1. So it has to alternate in sign. Okay. So after a 1, there can be zeros, but after that, there has to be a -1. There cannot be a 1 again. So you can see that all permutation matrices are actually alternating sign matrices, because permutation matrices have entries in 0 and 1 only, and all row and column sums are equal to 1. Since there are no other non-zero entries except 1, so the second condition is vacuously satisfied. So all permutation matrices are actually alternating sign matrices. For instance, there are 7 alternating sign matrices of order 3, which was also given by the formula in the previous slide. And these are the 6 permutation matrices that everyone knows, and the matrix given here. So the 7th alternating sign matrix would be something like this. And you can see that there is a -1 here. Except this, for n equal to 3, all the other 6 alternating sign matrices would just be the permutation matrices that everyone knows. So you can see the condition that if the conditions are satisfied or not in this matrix. So you can see that all the entries are 0, 1, and -1, and the row and column sums are equal to 1. So if you look at this row, the sum is 1. If you look at this row, the sum is 1, and so on. Again, in the columns, everything is 1. The sum is 1. And the non-zero entries, they alternate in each row and column. So for the first row, there is no -1. So this is satisfied because there is just only one. But in the second row, you can see that there is a -1. So after the 1, there is a -1. The sign alternates. This is a +1, and then it becomes a minus, and again it becomes a plus. So the alternating condition is also satisfied in this case. So I have already told that I'm interested in enumerating objects. If you are given certain structure or a certain type of combinatorial object, then my interest is the number of such objects. That is the enumeration of those objects. So the ASM enumeration conjecture, as I already mentioned, was given by Mills, Robbins, and Ramsey. And this conjecture was proved by Doron Zeilberger and independently by Greg Kuperberg. So it is very fascinating. This is a very fascinating part of mathematics history, because Zeilberger, he's a very famous discrete mathematician from Rutgers University. And if you don't know about him, I encourage that you go and read about him. So he has a very nice website where he posts Dr. Z's opinions, and I think these are worth reading. So they're very witty and very funny, and contains quite interesting mathematics. Anyway, so the history of this paper is quite interesting. So the full history can be read in Zeilberger's website. But just to mention very briefly, so Zeilberger submitted this paper in the early 1900s. In the early 1990s. And it was so he got back a referee report where the referee pointed out many problems with the paper. So he fixed those problems and then again sent it back to the journal. And again, same thing happened. So there were again problems, and then it went like this for 2-3 times. So the editor would send this back, and Zeilberger would fix and again send it back, and so on. And as a result, the paper grew to be very long. So Zeilberger had enough of this, and then what he did was he withdrew the paper from the journal, and then he rewrote the whole paper. So he rewrote the proof in a tree structure. So the previous talk was on graph theory. So if you know what is a tree, so you would know that each tree can have a sub branch, and then a branch can have another sub branch, and so on. So what Zeilberger did was that he divided his whole paper into a series of lemmas, sub-lemmas, sub-lemmas, and so on. And then the tree structure had like 7 different children. So sub-7 lemmas, and so on. And what he did was he gave that paper to several referees at the same time. So each referee was entrusted with reading and understanding only one particular lemma or sublemma of that paper. And when he collected all the reports, then he decided to publish the paper. So his paper was actually 84 pages long, so it's quite interesting. And the independent proof given by Greg Kupperberg was just 6 pages long. So Zeilberger actually he proved a stronger statement than the conjecture that I had shown before. And while Kupperberg exploited a connection with models from statistical physics. So mainly I work with the models that Kupperberg exploited. If there is time at the end, then I can show you a bit, but if not, then we'll just stick to getting into the results that are studied in this area. So let me go back to the alternating sign matrices once again and see how they were defined. So it seems to be a curious definition. So how come they define alternating sign matrices in that way? So there is another very nice piece of mathematics involved in that. So let us look at the matrix A, and we denote Aij to be the matrix that remains when the ith row and the jth column of A are deleted. Okay, so the subscript I denotes the column number, and the subscript J denotes the column number, and the superscript I denotes the row number. And if you have something like this, then it means that the ith row and the jth column of the matrix is deleted. And if we remove more than one row or column, then we'll just add in the superscript and the subscript and so on. So if there is like AIK, then that means I and kth row are deleted and so on. Okay. So then a very famous result in this area is the Denano-Jacobi adjoint matrix theorem. What it says is that if A is an n cross n matrix, then the determinant of A actually can be written in terms of determinants of smaller matrices which you get from A. So you can see so let me show you a better way. So in the right hand side, you can see that these matrices A11, ANN, A1n, AN1, these are all matrices which are smaller than A. These are n minus 1 times n minus 1 matrices, all of these here. And this matrix A1n, 1n, this is a even smaller matrix. So this is a n minus 2 times n minus 2 matrix. So that means what we have done is that the determinant of A we have represented in terms of determinants of smaller matrices. And if you write it in a compact way, then this is just this particular expression in the right hand side is just a determinant of this 2 times 2 matrix, and you just divide it by the determinant of A11, 1n. But there is a caveat in this. So if you notice, if this determinant becomes 0, then you cannot use this result actually. So this determinant has to be non-zero. But using some, but that is not very important for our case. The important part is that there exists a formula where you can write a determinant of a bigger matrix in terms of determinants of smaller matrices. So this is the important part. And this gives, as I said, this gives us a way of evaluating determinants in terms of smaller determinants. So Charles Dodson, who is better known as Lewis Carroll of Alice in Wonderland, he used this theorem, Denano-Jacobi theorem, to give an algorithm for evaluating determinants in terms of 2 times 2 determinants. So how can he do this? So if you use the previous result on a 3 times 3 determinant, suppose this is the determinant, this is the matrix that you want to find the determinant of. Using the previous result, you can write the determinant of this matrix in this way. Since if you delete the first and the last row and the first and the last column, there is only one entry remaining, and the determinant of a singleton matrix is just the entry itself. So you just divide 1 over A22 in this case. And then you just put in the formula from the previous slide to write the determinant of this 3 times 3 matrix in terms of determinants of 2 times 2 matrix. So we can go this one step ahead actually. So if you have a 4 times 4 determinant, using the previous formula, you can express this as a determinant of 3 times 3 matrices and 1 over a determinant of 2 times 2 matrix. But from the previous slide, you already know that all of these determinants, 3 times 3 determinants, can be themselves written in terms of 2 times 2 determinant. So all of these entries in this determinant is actually sort of like a product of 2 times 2 determinants. It is computationally very heavy, but the main point that I want to make is that any determinant of an n cross n matrix can be written in terms of determinants of 2 cross 2 matrices if you do the calculation properly. So that is the point I want to make. It is not computationally feasible, but it is a way to do this actually. So from this, in 1980s, Robbins and Ramsey, they looked at a generalization of these 2 times 2 determinant, which they call the lambda determinant. And how did they define the lambda determinant? So you have a 2 cross 2 matrix, and the lambda determinant of that matrix would now be, instead of a -1 here in our normal determinant, we put a plus lambda. So this will be A11 times A22 plus lambda A21 times A12. So instead of a -1 in our usual determinant, we will have a plus lambda here. And using the previous observations that determinant of any n cross n matrix can be written in terms of 2 times 2 matrices, we can actually use that observation to write any lambda determinant of a matrix n times n matrix in terms of the lambda determinants of 2 times 2 matrices. Okay, so it is again computationally not very nice, but you know that there is a way to do this. So that is the basic difference. So what would happen here is that if you had a lambda determinant here, instead of determinant, everywhere lambda determinant would appear. Everywhere you would replace this determinant symbol by a lambda determinant symbol. That is that lambda. Everywhere you would replace this, and then you put in the definition of the lambda determinant. So the main result that they proved, the interest of this was that they wanted a compact formula for the lambda determinant. So we know that there is a formula for the determinant which can be written in terms of permutations. So from there you get the permutation matrices that I mentioned in the second slide. So there is a way to write the determinant of a matrix in terms of the permutations. And similarly, there is a way to write the lambda determinant of a matrix in terms of the sum will run over the alternating sign matrices. Instead of the permutation matrices, the sum would run over alternating sign matrices in this case. So the formula that they gave was that the lambda determinant of a matrix A is now just a sum over all alternating sign matrices of order n, where they raise lambda to the inversion number. IB is the inversion number of this ASM B, and you have a bunch of terms where NB would now be the number of -1s in the alternating sign matrix. And then you have the normal product of entries in the matrix that you also have when you do the normal determinant. So probably I should have written the thing for the normal determinant, but anyway, it is not very difficult to see. So what you do is just, if you replace lambda by -1, lambda equal to -1, if you replace in this formula, then you will get back the determinant of the normal determinant that you were used to. But in that case, this term would vanish, because if you put 1 minus 1, then the sum would be over only permutation matrices. And in permutation matrices, the number of -1, so NB is the number of -1. So since there is no -1, this NB would be 0. So this term would really not occur in the formula. You would just have lambda, which is -1, so -1 to the power of inversion number, and then you will have a product of the entries Aij of the matrix. So Bij are actually the entries of the matrix B, and since in a permutation matrix there is no -1, so you can just remove this Bij actually. Okay? So this is how you would define the determinant of a matrix, and then you have the lambda determinant. So this was actually the first appearance of an alternating sign matrix in the literature. You can see that the sum is over alternating sign matrices. So this was how alternating sign matrices came to be defined. And a natural question was to ask how many of these alternating sign matrices exist, because we know that the number of permutation matrices of order n is just n factorial. So it was natural to ask how many alternating sign matrices exist, and so on. So let me just tell briefly what is the inversion number. So an easy way to calculate the inversion number of an alternating sign matrix is to look at pairs of entries. Okay, so you look at all pairs of entries for which one of them lies to the right and above the other. Suppose you are concentrating on this. You look at pairs of entries where it lies to the right and above. So this -1 will have a 1. We'll see a 1, and then you multiply the -1 with a 1, and there is nothing else. And here you see the -1, and you see a 1 here, and so on. So you do this for all pairs of entries, and you'll see that there are 7 pairs whose product is -1 and 2 pairs whose product is 7 pairs whose product is +1 and 2 pairs whose product is -1, and the inversion number would now be the sum of all these. So the inversion number would be 5, 7 +1s, and then you subtract 2 -1s and you get a 5. But this is not important for the rest of the talk. So just for completion of the talk, for the sake of completion, I am just mentioning this. You can forget about this after this slide. All this is very good, but how does one get a formula from this? So I mentioned that they conjectured a formula, and it was proven by Zeilberger and Kupperberg. But how does one conjecture such a formula? So first, let us have some observations. So this is an alternating sign matrix of order 4. The first observation is that there can only be one in the top row or the first column of an alternating sign matrix. Okay, so this is not difficult to see. Suppose there are two ones in the first row. Okay, so this is the first row. Suppose there are 2 ones. Then, because of the alternating condition, since the non-zero entries have to alternate in sign, there has to be a -1 in between those 2 +1s, right? So if you put 2 ones in the first row, then in some column there has to be a -1. Okay, suppose that column is the second column where there is a -1 in the first row. Now, if you look from the top of this column, since it starts with a -1 and the entries alternate in sign, the successive column sum, that means you add the first 2 entries, then you add the first 3 entries, and then you add the first 4 entries, and so on, would be, because it starts with a -1, the only possibilities are that it can be -1 or 0. So if there is a 0 below the -1, then the successive column entry would be -1. And if there is a 1 after that, at some point, there has to be a 1 because of the alternating condition. The sum would become -1 + 1, which will be 0. And you keep on going down in the column, and you will see that it cannot be anything else than -1 or 0. But the first condition of an alternating sign matrix was that the column sum has to be 1. And if there is a -1 in the top row, then that column will never have sum equal to 1. So that is why there cannot be a -1 in the top row. So because there is no -1 in the top row, and the row sum has to be 1, so there has to be exactly 1 in the top row. And because the matrix is a square matrix, by symmetry, in the first column and the last column as well as the last row, this condition is satisfied, that there can be only 1 in the top row, top row, first column, or bottom row, and the last column of this matrix, because of the symmetry of the square. So let us denote by A and K, this term, A and K, the number of n times n alternating sign matrices with a 1 at the top of the kth column. So here this matrix would be counted in A4-3, because this is a alternating sign matrix of order 4, and the third column, here the third column has a 1 in the top row. So this matrix would be counted in A4-3. So by A and K, I denote the number of n times n alternating sign matrix with a 1 at the top of the kth column. Okay? And some thought would give us that A and K is equal to n plus 1 minus K. So this is easy to see because of the symmetry. So this is a square, so it has naturally the dihedral symmetry. And if you flip it in the vertical axis, then you'd see that you'd get an alternating sign matrix again. So each of these A and K would correspond to something here, n plus 1 minus K. This is just a vertical flip. So you can think about this. So this is the symmetry. Further, if an is the number of n times n ASMs, then an1 is equal to an minus 1. Why is this true? Suppose the 1 is in the first row, in the first column. If the 1 is here, then there has to be all zeros here and all zeros here, because there cannot be a -1 to the left of this and below it, to the right of this and below it. So all of these will be zeros, and there will be a 1 here. So what we get is that in this case, in the 3x3 matrix that you would have here, this would be an alternating sign matrix of order 3. Because if you remove the zeros, and this 1 here, it makes no difference. The row sum and the column sum of this smaller matrix has to satisfy the alternating sign condition. So what you get in the smaller submatrix would be now an alternating sign matrix of 1 order less. So that is what is mentioned in this part. Now from here, this allows one to actually guess guess the formula from small values. So they first conjectured that a and k divided by a and k plus 1 is now given by something like this. So this is a rational function in n and k. This is a rational polynomial in n and k. And for discrete mathematicians, these type of polynomials are very nice, because this is an example of what you call a hypergeometric series. And once you have something like this, it becomes quite easy to understand the computation or how the series behaves and so on. So combinatorialists are very much interested in formulas of this type, where if you divide, then you get something very nice in terms of rational series in the variables that you are interested in. So once you have this, this gives us that this means that the a and k's are uniquely determined by the smaller a and k minus 1s. Okay. So what this means is that suppose you have a and k plus 1, if you take this to the other side, then this can be written in terms of a and k and product of this divided by what is in the numerator. So you see that a and k plus 1 is written in terms of a and k. Again, a and k can be written in terms of a and k minus 1 and so on. And you can go on up to a and 1. And once you reach a and 1, so a and 1 is now just the sum over all the k's from 1 to n minus 1, because a and 1 is just the number of alternating sign matrices of one order less, n minus 1, which I mentioned in the last part of the previous slide. So you see that a and 1 is now just a n minus 1. So what you have done is that basically you have written a and k plus 1 in terms of smaller a and k minus 1s. This should be k minus I actually. Anyway, so you have written in terms of a and k minus 1 and a and 1, which in turn is now written in terms of smaller values of a and minus 1 k's. Okay. So if you can determine all of these smaller values, then you can determine the bigger value. So you have like a sort of recursion, and using this recursion, you can actually conjecture a formula. So they did that, and Mills, Robinson, Ramsey, they conjectured that a and k is now given in terms of some binomial coefficients, and then product of factorial. So you see that this is the formula that was in the first slide, but that was the number of all alternating sign matrices. Now this is the number of all alternating sign matrices of order n, where the first row is fixed. That means in the first row, the only one which is possible is now in the kth column, and this is now the number of alternating sign matrices of order a n minus 1. Okay. So from here, knowing that a n is equal to a n plus 1 1, this allows us to conjecture an enumeration formula. So this is how the formula was first conjectured, and now I can tell you a bit more about why this formula was very nice. So suppose I have to guess some formula in the work that I'm doing, then what I would do is I would program my computer to output some of these values that I want. So suppose I have a bunch of objects that I want to count, and I'll program my computer to generate those objects, and then I'll count it for small values, because the computer cannot do really, I mean, it increases very fast, the combinatorial objects, most of the time. So at some point, the computer will stop. Say n equal to 10, it will stop. And then what I'll do is I'll look at the values of n equal to 1, 2, 3, up to n equal to 10. And then I'll do the prime factorization of all of those values. And if I see that the prime factors have small prime numbers, like for example, for n equal to 10, the formula has prime factors say 2, 5, 7, and 11 only, then I can hope that the final formula would be something like this. Because when you have a bunch of factorials, the prime there are a lot of prime factors which are very small, because of the way that these factorials are defined. So n factorial is just 1 into 2 into 3 into up to n. So once you have factorials, the prime factors, they are quite small. And you can, if you have like the small prime factors, then you can assume that you will have a nice cooking formula. So by that, I mean a nice cooking formula for me. So if the prime factors of the formula are low in some sense. So this is again subjective, but that is the idea behind this. Okay. So I already mentioned that the sequence in the title, it counts several different combinatorial objects, and one of these was the alternating sign matrices. So very quickly, I want to show that there show some of the other combinatorial objects which are counted by the same formula. So Zeilberger, we have already seen that he showed that this counts the alternating sign matrices. George Andrews is again another famous mathematician so who works in partitions and results related to Ramanujan's mathematics, he showed that another two classes actually of objects are counted by this formula. And very recently, Arvind Iyer of Indian Institute of Science, Ilse Fischer, who was my PhD supervisor, and Roger Behrem, who is my postdoc mentor now, they found another family of objects which are counted by the same formula. So first, I have already mentioned alternating sign matrices. Descending plane partitions are another class of objects which are counted by the same formula, and this was done by Andrews. Then we have something called totally symmetric self-complementary plane partitions, and then we have alternating sign matrices. So I'll just define these objects. I'll not do much with them. So let me very quickly go into what are descending plane partitions. So descending plane partitions are basically sort of like an array of numbers. So all these D1, 1, D1, 2, and so on, and D2, 2, and so on, all of these are integers, positive integers, and this is an array of numbers which satisfy certain conditions. The first condition is that all row entries are weakly decreasing. That means if you go along the rows, you will see that D11 is greater than equal to D12, is greater than equal to D13, and so on. So weakly decreasing means it is greater than equal. If it is decreasing, then it is strictly greater than, and so on. Okay? And all column entries are strictly decreasing. So this time, if you go from this column, this is just a single entry column, so you don't have to think about this. But if you go from this column, then D12 has to be strictly greater than D22. And then D13 has to be strictly greater than D23 and has to be strictly greater than D33 and so on. And this is a bit of a complicated condition. So what it says is that the number of entries in each row, if you look at the number of entries in each row, is strictly less than the first entry in the same row. That means this lambda 1 has to be less than D11. And in the second row, lambda 2 has to be less than D22. And lambda r has to be less than dr. And this is the first condition. And is at least as large as the first entry in this following row. So that means lambda 1 has to be at least as large as D22. Lambda 2 has to be at least as large as D33 and so on. So these are the conditions that a descending plane partition has to satisfy. So it looks very artificial, but in most of the cases that in many instances in combinatorics, many objects would look artificial in the first instance. But once you start to work with those objects, then you'll see that they appear in all sorts of areas and all sorts of different type of problems. So it is known that the number of descending plane partitions with entries at most n, that means the largest value, D11 is the largest value. So this entry, if it is at most n, then the number of such descending plane partitions are equal to the number of n times an alternating sign matrix. And this was proved by Andrews, in fact, way before alternating sign matrices were first introduced. So that means the sequence already existed, and only later it was found that alternating sign matrices were also counted by the same sequence. So another interesting object in combinatorics is what are called plane partitions. So plane partitions are nothing more than stacking a bunch of boxes in a room. So you can think of a room, the room that you are sitting in at the moment, and then you think of a corner in that room. So where two walls meet, you think of that corner, and you think that you want to stack some boxes of unit cubes. So you have a collection of unit cubes, and you want to stack those unit cubes in that corner. So how would you do that? You would put the first box in the extreme corner, that is in the 0, 0, 0 position. You'd put one box, and then you'd put the next box either adjacent to it. Either suppose you put the first box here, then you'd put the next box either adjacent to it here or to here or above it. You are not allowed to put that box in some other part of the room which is not adjacent. So this is like how you had in the talk yesterday about tilings by Anirban Roy, where he mentioned that there should be no overlaps and the whole region has to be covered. In our case, there has to be no gaps. So that means you cannot put one box here and then the next box you put it here and there is nothing in between. So that cannot happen. So plane partitions are actually ways of stacking these boxes in a corner of a room. And the mathematical definition is something like this. So a plane partition is an A times B times C box in a times C, A time B times C box is a subset of these entries. So what this condition means that I prime J prime K prime is in the plane partition if I J K is in the plane partition and I prime J prime K prime is less than I prime I J K. So this just means exactly what I said, that there can be no box which is flying above it, or there can be no box with empty space in between. So this is how you would visualize a plane partition. So there is another mathematical definition of a plane partition which you can write in terms of arrays, but I'll not go into that. So you already know what is a plane partition. Now let me tell you what is a totally symmetric self-complementary plane partition. Because of the way these objects are defined, these are like geometrical objects. So you would have symmetries on those objects. You can rotate this figure, and if the object has all the symmetries, that means it is same if you rotate it 60 degree, if you rotate it 120 degree, if you rotate it 180 degree, and so on. If it remains the same, and again if you reflect it along the axis, it remains the same. If you reflect it along, there will be three axes. This will be one axis, this will be one axis, and this will be one axis. So if you reflect along these axes, if it remains the same, then you will say that the plane partition is totally symmetric. Now the plane partition lies in a times B times C box. So you imagine that you have this A times B times C box, and you have this plane partition inside. So there will be something empty in that box. So all of these empty spaces, there will be something empty, and you can think of that empty part also as a plane partition. So that will be the complement of this plane partition. The empty part would be the complement of this plane partition. And if the complement of the plane partition is the same as the plane partition, then we'd say that the plane partition is self-complementary. That means it is the same as its complement. So these type of objects are called totally symmetric self-complementary plane partition, which plane partitions which are self-complementary as well as totally symmetric. That means it is same under all the symmetries. So this is what it says: if IJK is in the plane partition, if and only if all the 6 permutations of IJK are also in the plane partition. This means that it is totally symmetric, and the self-complementary part is explained here. Anyway, so what I want to focus is now that the class of these totally symmetric self-complementary plane partitions inside a 2n times 2n times 2n box are equal to order n ASMs. Okay, so this is another class of objects which are equinumerous with ASMs. Very quickly, let me go to the alternating sign triangle. So this is similar to an alternating sign matrix. Here again, you have entries in 1, -1, or 0. Along the rows and columns, again, the non-zero entries alternate. And the third condition is that the first non-zero entry from the top is a 1, and the row sums, this time not the column sums also, but the row sums is equal to 1. So let's look at an example. So this is an example of an order 3 alternating sign triangle. And it is known that alternating sign triangles are equinumerous with n times order n alternating sign matrices. So there are other combinatorial objects also which are equinumerous with alternating sign matrices, but we'll not go into them. And one of the major open problem is to find bijections between such objects. Actually, now there exists a bijection between descending plane partitions and alternating sign matrices, but this is it is called a signed bijection. It is slightly different from a bijection in the normal sense that you would think about. But one of the main open problems in this area of enumerative combinatorics is to find a bijection between all of these objects. So in combinatorics, you would be interested in finding bijections if two different type of objects are counted by the same number. So that is inherently a very enticing problem for discrete mathematicians and combinatorials. And one of the major problem is to find these missing bijections. So there has to exist some bijection, but nobody knows what this bijection is between the objects that I've shown today. Yeah, so as I mentioned, recently there was a bijective proof of the descending plane partition and ASM part, but it's a very complicated bijection. So I mean, yeah, it's a bit complicated. So it's like 40 pages long, and with a lot of computer code in between. So it's a bit complicated. But I would think that there would be something simpler. Okay. So does the story end here? We have explained ASMs and everything. Obviously, the story does not end here because I have so many slides left. So in the 1980s, Richard Stanley, he suggested that the various symmetry classes of ASMs are also very nice, and we should also study those. So remember, I told you that the alternating sign matrix is a square matrix, and it has the symmetries of the dihedral group. Because it is a square, you can think of the symmetries of the dihedral group. And Richard Stanley, who is very famous, who is a very famous mathematician, and he has some very nice books on combinatorics. So if you are interested in combinatorics, I would recommend Stanley's book, Enumerative Combinatorics, Volume 1 and Volume 2. These are like the Bible of combinatorics. Anyway, so Stanley suggested to look at the various symmetry classes of ASMs, and again Robbins conjectured several formulas. And I should stress that it was very difficult to prove the conjecture of Mills, Robbins, and Ramsey. It took about 15 years to prove that conjecture. And even now, we don't really understand the full picture of alternating sign matrices because there are several connections with different objects, different branches of mathematics, and there are several open problems which are still in this area. And even the symmetry classes, it turned out to be as difficult, even more difficult, because it took much longer to prove all these formulas. And only recently in 2016 was the last formula of this symmetry class proved actually. So let me briefly give you the symmetry classes. So you have the vertically symmetric alternating sign matrices where you would have something in the vertical symmetry axis, and if you flip it, it would be the same. By half-turn symmetric, you would rotate it by 90 degree, and if the matrix is the same, then it would be a half-turn symmetric ASM. Diagonally symmetric would again be a flip along the diagonal. Quarter turn symmetric, sorry, half turn would be 180 degree. Quarter turn would be 90 degree rotation. Horizontally and vertically would be the flip along the horizon, along the vertical and the horizontal axis. Diagonally and anti-diagonally would be along the diagonal as well as the anti-diagonal, which is the reverse diagonal. And all symmetry. So you see that in some cases I have written that there is no nice formula. In the other cases, I have written that Cooperberg in 2002 he proved this formula for vertically symmetric. Again, Cooperberg actually proved several of these formulas in a very classic paper that appeared in Annals of Mathematics in 2002. So Annals of Mathematics is generally considered to be, if not the best, one of the best journals in mathematics. And it is very rare for a combinatorics paper to appear in Annals of Mathematics, combinatorics of this style. So you can imagine that the problem was so important that it appeared in that journal. And then there was another very classic paper by Okada in 2004 where he proved other classes. And finally, in another very nice paper, Behren, Fisher, and Konvalinka, they proved the last remaining open case, which was the diagonally and anti-diagonally symmetric ASM case. And in some cases, there is no nice formula. And if you remember what I said in some time back, by nice formula, I mean a formula which can be written in terms of products of factorial or sums of products of factorial, and no such formula exists for these cases. It does not mean that there is no formula at all. It just means that the formula is much more complicated, and it is more difficult to prove such a formula if you really don't have any idea how to at least guess that formula. Okay. So it seems to be a nice moment to now stop for a few minutes and see if there are any questions. So Debasis, if there are any questions, you can. So far, I can answer some of them.
Okay. Okay, then if you want, we can take up one question here. Yeah, this is from Ashish Gupta. Do you have any formula to find eigenvalues of ASM matrices of higher order using small order matrices?
Oh yes. So this is a question that I get actually about eigenvalues and determinants of ASMs, and the short answer is no, because in terms of a linear algebraic perspective, these matrices are not as interesting as other matrices are. So not much work has been done, but I know that Richard Gruelli, who has written this nice undergraduate book, Introductory Combinatorics, Gruelli has done some work on eigenvalues of alternating sign matrices and so on. But in general, no. The answer is no.
Okay, so we can take another related. I think this is from Rohit Kumar. Is ASM related to Hadamard matrices?
Again, no. So think of these objects as purely combinatorial objects, and I mean it is difficult to appreciate a combinatorial object because I think no combinatorics is really taught in the undergraduate or master's syllabus in most Indian universities. But think of these as combinatorial objects, and in combinatorial objects, the object would be interesting if it has if it appears in several different areas in combinatorics and in other areas, but it has no relation to Hadamard matrices, as far as I know. There might be some relation, as far as I know.
Okay. Okay, then you can proceed. We'll take up other questions if they.
Okay,
yeah. Yeah, we can take up later.
Okay, so I'll go on for about 15 more minutes, and let me
Yeah.
see how much I can cover in those 15 minutes. So what I'm interested in are, so by the way, this picture was, I like this picture very much. This picture was taken in Marseille, where I went for a conference, and this is the nice Mediterranean Sea, and you can also see some of these algae here. So,
Oh yeah,
so it's very nice place. Anyway,
nice.
um, so let's look at the refined enumeration of ASM. So what do I mean by refined enumeration? So first observation that I already mentioned was that there is only one in the boundary row and boundary column. So this is now a order 7 alternating sign matrix. And this suggests the question that how many ASMs with the position of the one fixed. You can ask this question, that how many ASMs have the position of the one fixed in this row. Or you can also ask, like, how many ASMs have the one in the first row fixed here, as well as the one in the first column fixed somewhere here. That would also be a question that one would ask. And these are called refined enumeration of ASMs. So already I have told you that the first such formula of the refined enumeration was conjectured by Robbins, and this was proven by Zeilberger again in 1996. So where he found the number of alternating sign matrices of order n, with the first one in the first row at the kth column. So this is a mouthful, but anyway, so the notation is self-evident, I would say. And after that, several people have worked on this refined enumeration. And these are some of the names. So Roger Behren, Ilse Fischer, Dan Romik, Razumov and Stroganov. These were pairs of two Russian physicists who worked on several of these cases. Then Arvind Dyer, then Matan Karlinsky, who was a student of Dan Romik, and so on. And since the last 2 years, I have also been working on this area. And now I would like to show you some of these results that I proved. So last year we proved, along with Ilse Fischer, we proved actually four different conjectures. So one was a conjecture of Ilse Fischer, then there was another conjecture, two conjectures by Robbins from the late 1980s, which for some reason nobody looked at. And then there was a conjecture by Duchon from 2008, and we managed to prove some of these conjectures as well as many other results related to refined enumeration of alternating sign matrices. And let's look at some of these. So maybe I'll just do one case and then stop. So in case of vertically symmetric alternating sign matrix, we can make several more observations. The first observation is that they exist only for odd order. Why is this the case? So suppose they existed for even order, then the vertical symmetry axis would be in between two columns. So it would lie in between two columns. And because of the vertical symmetry, the sum of the entries to the left of that column would be same as the sum of the entries to the right of the column. That means the total sum of these entries in the row would be divisible by 2, because this sum and this sum would be equal. But in alternating sign matrix, we know that the first condition itself is that the row sum or the column sum has to be 1. So it cannot be divisible by 2. That is why the vertical symmetry axis cannot lie in between two columns. It has to lie exactly in a column, and this is only possible for an odd order alternating sign matrix. And once you have this vertical symmetry, because in the first row you cannot you cannot have two ones, so it forces the one to be in the middle row. So by the symmetry, it forces this one. And if you think for some time, I'll not give the explanation. It is not very difficult, and I encourage the students to think about this. That for a vertically symmetric alternating sign matrix, the middle column is always 1 minus 1, 1 minus 1, and so on. So you can see here it is 1 minus 1, 1 minus 1, 1 minus 1, and so on. So this middle column is always fixed. But once you have a minus 1 here, there has to be at least two ones, which has to be 1 has to be to the left of this, and 1 has to be to the right of this. And because the first row has only zeros, there cannot be a minus 1 here, because remember, the first non-zero entry from the top of any column has to be a 1. It cannot be a minus 1. Okay, so what you see in the second row is that the second row has exactly two ones, and these are placed symmetrically with respect to the middle minus 1. So it is symmetrically placed to the left and to the right. So in this case, we can ask a refined enumeration question with respect to the position of the ones in the second row, because in the first row it is always fixed. So the question is not very interesting. So if we ask this question, and Fisher did that, and she conjectured that the number of odd order vertically symmetric alternating sign matrices, where the first one in the second row is equal to something like this. This is the product formula. So she conjectured this in 2007. So if you go back, you will see that in the first column, there is no such restriction. The one can appear, it cannot appear here because the one already appears here, but it can appear in any of these positions except the last position. Again, in the last position, the one has to be in the middle. So the one in the first column can appear anywhere in between. And this also gives rise to a different refined enumeration question. And this was studied by Razumov and Stroganov in 2004, where they proved that the formula for these type of numbers, 2n plus 1 times 2n plus 1 order alternating vertically symmetric alternating sign matrices, where the first one in the first column appears in the ith row, is given by something like this. You can see that this is a more complicated formula because there is a summation. And Fisher conjectured the other part, where she was interested in only the second row. And last year we proved the formula of Fisher. So working together with Fisher, we proved this formula. So that actually this formula is correct. And a bijective proof of this last relation. So this formula has actually connections with the previous formula. You can write this one as a sum of two of these numbers actually. So these are 2n plus 1 I and 2n plus 1 I plus 1. And again, a bijective proof of this would be of great interest because our proofs are not bijective in nature. So what about the other symmetry classes? I mentioned that there are several other symmetry classes, and for many of these, actually for all of these except the diagonally and anti-diagonally symmetric case, except for one case, we have managed to prove all of these refined enumeration results. So you can have something called vertically and horizontally symmetric, where you have the vertical symmetry as well as the horizontal symmetry. And in this case, the middle column is fixed as well as the middle row is fixed. But you can ask the same question, what happens in the second row or the second column? And the formulas in this case are a bit more complicated. So this is now given in terms of a generating function. We don't have a explicit product formula, but it is given in terms of a generating function. And the terms that appear in the generating function, so this is a bit complicated, and if you are not really used to such type of results, then you would not appreciate this result. But this is a nice result in the sense that we are interested in these numbers that appear in the right hand side, and these numbers that appear in the right hand side can be written in terms of the numbers that appear on the left hand side. And this AVC, this number I have already shown in the previous slide, this we know. The QNI, this we could find out what this QNI means. And let me show you if I have the QNI. Maybe I don't have it. Yeah, okay. So I don't have the QNI, but the QNI are again written in terms of sums of factorials. So this is known, and to find this now we can just compare the coefficients of z, powers of z, and we'll get this. So this is one generating function for the vertically and horizontally symmetric cases. So I can skip this. This is another class of alternating sign matrix for which we have some formulas. And let me go now to something called quarter-turn symmetric, because those formulas are much nicer. So quarter-turn symmetric, as I already mentioned, are alternating sign matrices that are invariant under a 90-degree rotation. And it can be seen that these matrices do not occur for order 4n plus 2. So I'll not do the proof, but it is very easily you can see that this does not happen for order 4n plus 2. So Robbins, he conjectured refined enumeration formula for all the other orders. So you have modulo 2, you cannot 2 modulo 4, you cannot have any quarter-turn symmetrization. But for 0 mod 4, 1 mod 4, and 3 mod 4, you can have quarter-turn symmetrizations. And Robbins conjectured some formulas for these enumeration of refined quarter-turn symmetrizations. And we proved all these formulas. So, for example, when you have a 4n order quarter-turn symmetric then the generating function of these numbers, the refined numbers, can be written in terms of numbers that we already know. So here, this ANI and AHT2NI, we already know. I have not written the numbers, but we already know. So actually, I have these numbers. Okay, so here you have. So ANI is now something like this, and AHT2NI is a bit more complicated, but still we know what these numbers are. Anyway, so I can actually skip this quarter-turn symmetric case and then show you something else. some other type of refined enumeration, some other type of enumeration results that we can study for alternating sign matrices. And this is called the 1 over n phenomenon of quadrant symmetric ASMs. So the central entry of a order 4n plus 1 quadrant symmetric ASM is always 1. And you can prove this. It is not difficult. So how do we do this? So let this be a quadrant symmetric ASM of order 4n plus 1. Then we look at the central entry. So we are interested in finding out what the central entry is. Remember that the entries can only be 1, -1, or 0. So since it is quadrant symmetric, everything that appears here is symmetrically appearing here, as well as it is symmetrically appearing here and here. So except these middle portions, all of the other portions, the things that appear in this part are the same as the things that appear here, are the same as the things that appear here, and so on, because of the quadrant symmetry, which is the 90-degree rotation symmetry. So it follows that the sum of these entries times 4, so will be the sum of entries here, sum of entries here, sum of entries here, and sum of entries here, plus the sum of entries here in this middle part. If you multiply it 4 times, then you will get the sum here, and sum here as well, plus the middle entry. All of this particular expression in the left hand side is actually the sum of all the entries of the quadrant symmetric ASM. And we know that since the row sums are equal to 1, so the total sum of all the entries of a quadrant symmetric matrix of order 4n plus 1 must be 4n plus 1, because each row will contribute 1. And once you have this, you will see that this is something which is divisible by 4, and you have something here. So you can immediately conclude that this star has to be a 1. So this part will be equal to this 4n, and then you will have the star will be equal to 1. Similarly, the central entry of a quadrant symmetric ASM of order 4n plus 3 is always a -1. So for 4n plus 1, it is 1, and for 4n plus 3, it is -1. Okay. And because of the symmetry, all adjacent entries of this central entry are the same. That means this entry here is the same as the entry that appears immediately below this, as the same as the entry that appears immediately above this, and also to the right. So all of these entries, because of the symmetry, quadrant symmetry, it is the same. Now the question is, the proportion of quadrant symmetric matrix of appropriate order, either 4n plus 1 or 4n plus 3, with fixed entries adjacent to the central entry, was conjectured by Stroganov to be n plus 1 divided by n. What it means is that this entry, the a 2n plus 1 2n, as well as this entry and the one below this and the one above this, are either 0 or -1. So it cannot be 1, because the 1 is the central entry. So this entry has to be 0 or -1. And Stroganov, he conjectured that the proportion of entries where it is 0 divided by the number of matrices where it is -1 is given by a very simple ratio, n plus 1 divided by n. And this phenomenon was already observed in the case of other matrices by different people like Aval and Bouchon, Razumov and Stroganov, and Behr and Fisher and Konvalinka for other classes of symmetry. And this is called the 1 over n phenomenon in ASM. And for all the other cases, it was already proved, except the case for the quadrant symmetric ASM, which was not proved for some reason. And recently, we managed to prove Stroganov's conjecture for the quadrant symmetric ASM as well. So what this theorem states is the following. So if you let the number of quadrant symmetric ASM of order n with entries adjacent with central entry being star, that means if the entry adjacent to the central entry is 0, then we have a qt 0. And if it is -1, we have a qt -1. This is valid for order 4n plus 1, because the central entry in a order 4n plus 1 quadrant symmetric ASM is a 1. So Stroganov's conjecture was this, that the proportion of entries with a 0 adjacent to the central entry to that of the proportion of ASMs with a -1 to the central entry is n plus 1 divided by n. And in case of 4n plus 3, it was so the central entry was a -1, so the proportion was between 1 and 0, and this was n plus 1. So recently we managed to also prove these results. So this is another type of enumeration result or enumeration technique that we are interested in ASMs. So this is just the tip of the iceberg. There are several different problems that you can study in ASMs, and some of these I'm interested in, and some of these There are other people who are doing this kind of work, and there is a very nice book called Proofs and Confirmations by David Bresso. If you are interested, you can look at that book. So let me just end my talk here, and over to Devasis if there are any questions.
Yeah. Thank you very much, Manjil, for the wonderful presentation. We have some questions here, but before that, yeah. Okay, can you please close the screen sharing so that you can, you can also see the questions popping up. Yeah. Okay. Can you see the comments as I click?
Yes,
Is
yes.
it popping up on your screen? Yeah.
Yes.
Okay. So first of all, I'd take some feedback from our other speakers. Kollolpal sir, you are live on screen now, and Sujit Dev sir also. He is also there with us, and Anirban sir, I think is there. Okay, so I'll go to Kollolpal sir for some feedback.
Nice presentation. I don't want in combinatorial things, but it's a very nice presentation. But I have a little connection with this linear algebra type of things. I work in functional analysis, and these finite dimensional things are basically linear algebra. So just I would be interested in this. Is there any this ASM matrices a very simple way of looking into their eigenvalues or something like that?
Yeah. So as I mentioned in between, so for me, I'm a discrete mathematician. So for me, it has no interest yet. But I know for sure that Richard Bruelli has done some work on eigenvalues of alternating sign matrices.
Bruelli is a big man. Yeah, I know. Yeah.
So Richard Bruelli has some papers in this area.
Some papers on that. Yeah. It's very nice presentation. Thank you. Thank you, Devashish, also.
Thank you, sir. We are also eager to listen from you tomorrow. So for the participants, you can join us tomorrow for Kollolpal sir's lecture. He is from Jadavpur University, Kolkata. He works on functional analysis.
Yeah.
And he is a very, very good teacher, very good researcher. So we are all looking forward to his talk. Thank you, sir.
I justice to your comments.
Obviously, sir. So I'm putting you backstage now. I'm going to Vishwajit, sir. Yeah, Vishwajit, sir.
Manjil, thank you for looking at this new ideas. This is first time I'm coming across of ASMs. In fact, I will now during your talk only I was thinking and how graph can be associated with this. So I definitely would like to go forward and see if any connection is there with graphs. So what about you? Is there any connection with graphs of this ASM matrix?
With graphs, not directly, but there are connections indirectly with graphs.
Am I audible, Manjil?
Yes, sir. Yes. So with graphs, there are some indirect connections of ASM, but it would be too far removed from my talk. So maybe we can discuss it privately at some point. I think his approach is a bit.
Yeah, probably. Okay, so we have some more questions here. Yeah, there was one question in between. Yeah, this one you can share. Maybe it was in reference to some of your slides. Is lambda any arbitrary number, or does it have any fixed value?
So lambda is any arbitrary non-complex number. You can take to be any complex number actually.
Okay. Okay, and yeah, this is another one you can see. I'm not sure if I missed any details first time with this concept. From the slide title, how does one get a formula from this? What if we swap R1 and R3? -1 can be there in first row, unlike this claim. Yeah.
So what do you mean by R1 and R3?
Maybe he means row. I think row 1 and row 3, or what?
Okay. Yeah, okay. Suppose you swap the row 1 with row 3, then you don't have this alternating condition. So you can have the alternating condition, but if you have the alternating condition, then you will actually violate the row sum equal to 1 condition. So then the row and column sum equal to 1 condition will be violated if you swap the row 1 with 3.
Okay, so we have, I think, the other question I had already placed. Oh, this question already we have taken up. Do you have any formula for finding out? Yeah, this we have taken. Let me see if there are any other. Yeah, this is one. It's probably a general question. Yeah, is Ramanujan a discrete? Discrete
Well,
mathematician. Part of it, his work is in discrete mathematics.
well, for me, he's an analyst and a number theorist. So his work in discrete maths is basically his work in partitions. So partition theory would be what we would call discrete maths. But even then, I don't think he had any combinatorial proof or any combinatorial description of any of his results. Everything that he did was using analysis and number theory.
Yeah. Okay. So there are some feedback, and yeah, there are no more questions as of now from the participants. Yeah, Anirban now has joined. Let me bring him on screen. Yeah.
Hi,
Hi.
Dr. Saikia. This is what comes to my mind. I was ready to speak in the beginning itself. I mean, because just flowing in my mind is commendable. Hats off, brilliant.
Thank you.
This is what I was thinking. I mean, I have a humble request to you. If you please share the slide to me, probably after this talk only, because I want to. I'm doing. I was in the process of doing something. It
Sure.
would be really a big help for me. Okay.
Sure.
Kindly share that. You have my mail ID.
Yeah, sure. I'll share it. Actually, I'll share it with the doctor as well. Because I did not have time, but towards the back of my slides, you can actually read some of the proof techniques. I mean, it assumes some background of representation theory as well. But I mean, if you are motivated, I think, like for the participants, if they are motivated, I think they can also read some of the proof techniques towards the end of the slide. So I'll share it as well.
Sure. I just want to add that because I think probably Dr. Manjil will be knowing I'm writing something, not writing. I'm trying to figure out something. So I think it could be a big help for both of us. I mean, down the line. Okay. One question I want to ask is that as you are telling now, you started, I'm a discrete mathematician, saying like that. And just now one of the participant also asked about that Ramanujan and this thing, and that analytic number theory has come into picture probably. So basically there is something like a hypergeometric series and Ramanujan's P series that you work usually. So so I hope we can go. I mean, it is not like that the discrete mathematics cannot cater into that area. I mean, is there any fair difference or bifurcation like that? It can be anyhow.
No, actually, like the series thing that you mentioned, this falls under something called special functions, and that is something which I use quite often. Actually, for example, hypergeometric series I use quite often in my work. And some of these formulas actually has a hypergeometric function relation. I mean, you know already because I mentioned this to you. So my previous love was in number theory, and then I shifted to discrete maths. But I still like to discuss connections between these two subjects.
Good. In fact, probably I had a talk in last June, last year June, when we had a better situation. I was giving a talk on Salem number.
Okay.
Salem number, and of course I was trying to give an expository talk on Salem number and Pisot-Bijaragan numbers.
Okay.
Those are very fascinating numbers. I mean, for me, numbers always excite me.
That is true, yes. So, for example, Pisot-Bijaragan numbers are quite interesting and quite fascinating actually, and they have a lot of connections with discrete maths.
Yeah, and that yesterday, I mean, during my talk, I didn't enter to that area, that Penrose tiling. I mean, the moment you go to aperiodic structure, you have shared that today, that even that paper. So in that Penrose tiling, no, it is ultimately giving that Vijay number also coming into picture. So it's so fascinating to see all these things and globally meeting one another one. It's really attracting. So to start from where I started, commendable job. What a nice presentation and what a nice work. Hats off to you.
Thank
All the best.
Thank you.
Thank you, Dr. Devashish.
Yeah, thank you, Anirban sir. I have means we have two more questions here. One is a general one. Yeah, this one probably related to one of your slides. What can be the values of lambda in the lambda determinant?
So as I said, you can take them to be complex numbers, but maybe it is easier to work with integers.
Real integers. And this is a general question. Okay, yeah, maybe you can have some comments on this from Anurag Sawa. I have a general question. Why linear algebra is called linear?
Well, I'm not so maybe Devashish is a better person to answer this, but I think the word linear comes because it concerns with linear equations or linear
Yeah,
math.
yeah. Okay, for this this is a very common question students ask. So I'd ask to ask the participants to have a look at Professor Kumarasan's book on geometric approach to linear algebra, or any other linear algebra book. You will have detailed discussion about the relation between linear algebra, linear equations, geometry, and all. Okay, and let me see if okay. Yeah, this is again could find the speaker's name cited in OEIS or Encyclopedia of Integer Sequence, right? Page
Yes.
for the sequence in question. Thank you for the wonderful introduction. Okay, good.
Yeah, so OEIS page has also a lot of nice papers connected with ASMs. You can find
Yeah.
a good bibliography.
Okay. So some comments for you. Always get some comments.
Thank
Okay.
you.
So overall, it was a nice session. Thank you very much,
Thank you.
Dr. Saikia, for your presentation, and thank you for being with us. So in future also we'll connect with you. In fact, we had connected with you twice. The earlier two webinars by Professor Suri and Professor Shantalastram was through your website Ganitswara. So for the information of participant, I would also like to request Dr. Manjil to say something about the mathematical website, which of which he is the co-founder. Yeah.
Yeah, well. So you have already mentioned about Ganitswara. So I would ask everyone to visit the website and give us their feedback. So Devashish is a very regular contributor as well as a member of the team of Ganitswara. And since June, we are conducting some webinars. So every Saturday or Sunday, we do this. So the next webinar is tomorrow, and it will be by Professor Geeta Venkataraman of Ambedkar University on group theory. So these would be nice if the students would like to attend some of these webinars, because we are trying to invite well-known people from India as well as abroad. So to give some introductory talk. This will be very introductory, actually, no research level talks, only introductory topics from BSc syllabus.
Okay. So I have provided the link to the website also. It's correct, no?
Yes.
Yeah, Ganitswara.com. Yeah. So
my
participants
email ID is manjil@ganitswara.com. If anybody has any.
Yeah, I can just mention that also. Manjil@ganitswara.com. Yeah, manjil@ganitswara.com. So if you are interested to contact him, you can contact him through this email ID.
So
Okay.
I see a question of Bijita Paul, which asked about dot-com condensation.
Yeah. There is a question which has come up.
I think it is better that I'll send the slide to Devashish and you can send it to the participants and then they can take a look at it.
Okay, one last question. If you might not bother to answer, how is Dodson? Okay, you'll send the slide. Yeah.
I'll
So
send the slide and I'll give a reference to this answer.
Yeah, he will share the slide so I can send it to the participants. Okay, we also have a comment from our mentor, Professor M.B. Rege from Northeastern Hill University. He has been an inspiration to many of us here in Northeast and all over India as well. So thank you, sir, for your comment. Great to know that such an interaction is taking place. Thank you, sir. Thank you very much. Okay. So with this, we have come to the end of the third session for today. And tomorrow we'll have the final session by Professor Kollal Pal. So I request the participants to join us tomorrow also. And once again, I would like to thank Dr. Manjil Saikia. And I would like to end the broadcast now. So I am closing the live session now.
Thank you.